Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speakers your questions from the chat window. Your questions in the chat window will only be visible to myself and our speakers. So with that, thank you for joining us today. It is now my pleasure to introduce our speakers, Josephina Nielsen and Gustav Kalberg from Vironova.
So thank you, Leah, for the introduction. Gustav and I today will talk about new approaches to subvisible particle characterization. So first, let me give you a short introduction to how we do this by combining electron microscopy and image analysis here at Vironova. Here, in-house, we have a large group of experts in interdisciplinary fields like electron microscopy, image analysis, programming, and structural biology. So by combining this expertise with our in-house developed software, we are able to offer these kind of analysis as a service. However, after discussions with our partners and clients, we have understood that we need to make this technique and method available for our clients, for them to be able to do this in-house. And from that, we have developed a tabletop transmission electron microscope, which we then call the Minitime system. And that is what we will talk about and show you examples from today. So why at all use electron microscopy? That is because particle characterization or characteristics like the size and shape and purity of your sample can often be directly correlated to the efficacy and safety of your product, which is of course important. So electron microscopy is really a good technique to get to know your product in detail and to understand your design space, like what happens if I change my formulation or purification process in one or the other way. And for all of you that are working with, for instance, viruses and proteins, the process to get your product is quite complex. And there are a lot of parameters to keep track on, of course, like, for instance, aggregation that you would not like to have due to unsuitable up or downstream conditions. The trade-off during purification, for instance. I mean, you don't want to lose your product, but still get a pure sample. And, of course, to make sure that your particle has the right morphology and are intact also over time and storage. So there is a lot of parameters to be monitored where we think that the Minitime system could be very helpful. So Gustav, please let us know a little bit more about what we have done to make the Minitime system more available.
Yes, so on this slide I've put a conventional electron microscope on the left side and the Minitime system on the right-hand side. And I've listed a few key properties of the two different systems. A conventional electron microscope is built for experts by other experts. It means that you have a very high skill level and needed for operating this intricate system. You can gain really high magnification, resolutions of below half a nanometer. It's an established technique, so there's a lot of publications and a large community around the systems. However, the high level of expertise needed is a problem. Also, there is a problem with the adaptive facilities needed for the system to run. You need to have a very stable floor to get rid of vibrations and also to keep up with the high load. You need to have running cooling water. You need to have three-phase power outlets and a lot of infrastructure around the system. There's also high maintenance costs and a lot of downtime due to maintenance and also different issues that can arise with such an intricate system. The Minitime system, on the other hand, is designed for generalists, and the reason for making this system so easy to use is the small size and lower acceleration voltage, which makes it possible to get a less sensitive system, still with a high magnification, resolution of 1 nanometer. And due to the small size, we're able to control this microscope automatically. So there's only a few parameters necessary for the user to deal with. And the whole system runs on an ordinary wall socket, 230 or 110 volts, and no cooling water or other cooling systems. So you can place this in an ordinary lab setting. I would also like to describe the Minitime system in comparison to other established techniques for nanoparticle characterization. And most of you are probably familiar with the indirect methods such as DLS and NTA. These methods, it's indirect, so you get to measure properties of your samples even though you don't get information about individual particles. You can turn to conventional electron microscopes to gain the extra depth of information, to be able to see individual objects and measure these objects in the images. It will also be able to see the morphology of the particles. But the conventional electron microscopes are very complex to use. They are high maintenance and so on. So there is actually a huge step in between these methods in terms of the threshold for a user to take. And then we have the Minitime system, which is less complex to use. You still gain the same type of information as you do in conventional electron microscopes. You can actually even gain more by automating the analysis, which is what we will show further on in this presentation. To illustrate this property of the Minitime, we ran a sample of a AAV sample through a DLS and the Minitime system for a standard size distribution or size analysis. The DLS shows a very broad peak. That's the blue peak in the plot here. You have a median value on the expected 30 nanometers range. The Minitime system, on the other hand, shows you 2 distinct peaks. And when you turn to the images, you can actually see that you have 2 distinct classes of particles, the AAV particles and a smaller shape, donut-shaped particle, which are actually proteasomes. You can see the donut shape from one side and the barrel shape, the side of it in some of the images. Josefina?
So yeah, one of the nice things here with the Minitime system is then that it's not a black box. The day that you might get unexpected results, you can actually go back to the analysis, look at the structures behind these results, and then start to understand what have actually happened. And as we said before, there are a couple of parameters that we normally want to keep track of, like, for instance, the particle morphology and integrity. So this can affect the product efficacy and also give us insight of the stability of the product. The level and size of aggregates, of course, as that might give us unwanted immunogenicity, and also then the level of debris, the purity of your sample, as that could be a nucleation site for aggregation. So let us show you a couple of analyses that we have done regarding these 3 parameters, starting with the morphology. Here you see, again, images of adenoviruses. On the left-hand side, you have an image from a conventional electron microscope, and on your right-hand side, you have an image from the Minitime system. And here we can see in both images the adenovirus particles, of course. You can see the surface proteins and also the icosahedral arrangement of the protein. But we can also see structures in the background. that comes from broken adenovirus particles, like the donut-shaped hexons and the fiber structures, which is normally found in the five-fold axis of the virus. So you can indeed use the Minitime system to also analyze these kind of small structures. But sometimes, of course, you want to get more quantitative data to be able to compare different samples with each other. So please, Gustav, show us how we can do that.
Yes, so when it comes to measures which we don't want to base on single images, so morphology we can look at individual images, but quantitative measures, then we need to look at multiple locations of the sample and acquire many images to measure a large number of particles and objects. And we do this in the Minitime system by automating the image acquisition as well as the image analysis. So this illustration shows you the overview of a grid to the left. The center image shows you a location where we have acquired an array of images, and to the right an example of one detected or analyzed image where we have found, it's actually in this case adenoviruses. So the yellow ones are adenoviruses, and we have estimated amount of background debris with the red object. And we do this on hundreds of images and detect tens of thousands of particles, and then we can get robust quantitative measures. One example is to look at the aggregates, as Josefina mentioned before, which is of great interest. In this case, I show you a size distribution to the left, showing the diameter of each object detected. The red large peak is the background debris. You see a small yellow-orange contribution, which is the adenoviruses. And then you also see one outlier to the right in the distribution, which is actually an aggregate. And the nice thing with the Minitime system is that you have both the concluded size distribution, but also all the image data. So I can go back from this outlier and look at the actual aggregate and see if I can get the pointer. I can show you here to the right on this image this specific aggregate showing up in this peak in the size distribution. The next on the list was purity and the amount of or level of debris. And this is also a perfect analysis for the automation in the Minitime system. So we conducted the same approach I showed you before. And then we have measured the relative purity from two different samples. We measured the purity by looking at the ratio of the area between the class of adenoviruses and the background debris. So we have a plot to the left. You can see the distribution of relative purity between the two samples, and the images are fits well with what we manually perceive as a clean or pure and not as pure sample. So in this way, we can get the quantitative measure of purity. You can start to rate and order your samples in terms of purity. Another very nice property of this analysis is that the high degree of automation makes it very fast. We have compared this analysis to how long it would take to do it all manual. So we did the same analysis on 20 images, and then we extrapolated the amount of time it would take to do this on all, I think it was about 200 images. And you can see that using the Minitime system, it takes less than 10 hours. Using a conventional EM and doing the analysis manually, it would take almost 80 hours in total. And yes, I think I will give the word to Josefina.
So to summarize, by having the Minitime system then at your site, you will be able to do detailed characterization on your product, which in early development, which can of course support both the formulation and production process. And which is really important then is to identify the critical and measurable parameters in early development and use them throughout the whole process, which could again then give you a really robust process and high quality products. So I think that was what we wanted to show you today. Thank you very much for listening. And if you have any questions, we are more than happy to try to answer them either here in the chat room, or you can of course contact us directly. Thank you very much.
Thank you.
Thank you. So we do have a couple questions from the audience. The first one is, how are liquid samples analyzed by the Minitime?
So in using electron microscopy, we fixate the sample. So you take a small volume of your liquid sample, about 3 microliters, and you put it on a sample grid, and then you add staining, and then you let it dry, and then you can analyze the sample. And that process takes maybe 15 to 20 minutes, roughly.
Not even that, but it's really short.
And can you comment on the footprint size of the instrument? And is it intended to be a benchtop instrument, or does it sit on the floor?
So you can have it in different configurations. The current setup is that you have a table. You have some control electronics beneath the table, and then you have the small unit to the side of the table. But it's also possible to as we show on the last image here, to have it in a even more compact design. But it's you get a small bench, and then you have your table where you have your screen and computer.
And can the system be used for pigment particle analysis?
If the pigment particles, I mean, are in the nanosize range, of course, then it should be possible.
Okay.
It's more term of the, sorry.
It's more a term
no, go ahead,
of,
Gustav.
It's more a term of the electron density of the particles.
Okay. And is the system capable of analyzing the purity of influenza virus particles?
Yeah, we have a good experience of influenza particles, so that should be will work fine.
Okay. And how much sample volume is needed to perform the analysis?
So the sample volume you actually put on the grid is only 3 microliters. So that's what's necessary. So a small droplet.
Okay. And are the specimens negatively stained?
Yes, they are.
Yeah. You can actually run it even without stain for some specific application.
True.
But generally negative stain.
Okay. And what is the resolution of the microscope?
So it's measured to just below 1 nanometer. That's the resolution.
Okay. Well, thank you very much, Gustav and Josefina. And thank you to our audience for your questions and for joining us. The recorded version of this webcast will be available for on-demand viewing on our website. And as a registered attendee, you will receive a follow-up email providing you with a direct link. So thank you. And we look forward to having all of you join us at our future BioProcess International Ask the Expert webcasts. We have a full lineup covering many aspects of bioprocessing scheduled for the duration of the year. Look for those announcements in your inbox. Thanks again.